Hello there, this is Jude Socrates. Welcome to Multivariable Calculus. This is video number 21 in my series for Math 5C at Pasadena City College. So we have been doing triple integrals, and today we are going to see a way by which we can compute triple integrals using an idea from chapter 2, and namely that is using polar coordinates. But now that we're doing triple integrals, for some reason we like to call them cylindrical coordinates instead of polar coordinates. But the idea is exactly the same. Okay, so I will see you in a minute. We will continue on page 154. All right, so for the first part of this video, we're going to walk through the concepts and the two examples that I have over there, because I want to show you the GeoGebra diagram that I created for that second example, which is a little bit complicated. So the idea to compute a triple integral in cylindrical coordinates is to change two of the variables into polar coordinates. Okay, so typically we've been using x and y to convert into r and theta. As usual, x is r cosine theta and y is r sine theta. But remember that there are 6 ways by which we can create an iterated integral, triple integral. Okay, so there are 3 pairs of variables that we can use to change to polar coordinates. We can use x and y, in which case z will depend on x and y. We can change x and z, in which case y will depend on x and z in the inner integral. Or we can change y and z, in which case x will depend on y and z. Okay, so of course we call this a type xy solid, a type xz solid, and a type yz solid. Okay, so we now have 3 choices to perform this conversion formula. Okay, so let's continue with this conversion. How will that affect the triple integral? Okay, so as usual, we will have a double integral outside, and that dA will of course be dx dy, and our inner integral is in z. Okay, so this is the type xy setup. You have a surface below and a surface above. All right, what is going to happen to this triple integral? Okay, so we will assume now that D is a polar region, so theta will go from some alpha to beta, and R will go from some A to B. Does it matter if theta is outside or R is outside? There are instances, as we saw in chapter 2, where R sometimes depends on theta. Okay, so we saw circles, for example, which are centered on the x-axis, but not on the origin. Okay, so those look like r equals 4 cosine theta, let's say, or r equals 6 sine theta. Okay, so it's usually safer to put theta on the outside of the integral. Okay, and perhaps r will depend on theta. Here it's just a polar rectangle. Okay, so what's going to happen to our limits? Right, so in the limits, we have to convert x and y into r and theta using our conversion formulas up here. Okay, so you will have a surface below expressed in terms of r and theta, and another one above. Same thing. How about the function? Okay, we have an integrand, f of x, y, z. So we will also convert x and y in the integrand into r and cosine, and r and theta. So essentially, x and y have completely disappeared, and you're left with r and theta. Z is still there. Okay, so z does not depend on x and y in the function, in the integrand that we are integrating. Okay, dz does not change either, of course. Don't forget that there's an extra r with the RDR, okay? So think of this as a package deal, okay? You have RDR d theta, okay? And of course, when we start to integrate this, the r will go inside our integrand, Okay, so what about the other possibilities? What if it's x and z or y and z? So you have to look at the view that you are using to make the conversions. Okay, so if it's x and y, we look from the top. And as usual, x should be on the right, y should be going up. Okay, so if it's y versus z, for example, we should be looking from the front. Y should be on our right, Z should be on the top. So this time, Y will be R cosine theta, Z will be R sine theta. Okay, what if we have an X versus Z? So we have to be looking from the side, stand on the left side, the negative Y axis. Make sure the x-axis, positive x-axis is to your right, positive z-axis going up as usual. Z is always up because, nobody stands on their heads unless you're into yoga or whatever. Okay, so be very careful with how you look at the solid. All right, for our first example, I hope you remember this solid. Okay, back in chapter 2, we computed the volume of this solid using polar coordinates, of course. Okay, so it's a paraboloid, z equals 9 minus x squared minus y squared, but we cut it off at the xy plane. Okay, and of course, the top view of the solid is just a circle. Okay, so where do you intersect the xy plane? When z is 0, we'll get x squared plus y squared equals 9. So of course, that's a circle of radius 3. All right, so we are going to compute this triple integral 3x squared plus 4z over this solid. All right, so the top view is, of course, obviously a circle, a disk. So we can parameterize that, we can convert to polar coordinates. As usual, x is r cosine theta, y is r sine theta. Theta is going full circle, literally 0 to 2 pi, and r is going from 0 to 3. Okay, so those will be the limits for our polar coordinates. All right, so to complete the setup, we will need the z coordinate. So of course, we're going from the xy plane up to the paraboloid. So that is going from 0 to 9 minus x squared minus y squared. So we also have to convert x and y in our limits. So of course, x squared plus y squared is just r squared. So we get 9 minus r squared. Okay. So finally, we have to convert the integrand as well. We have 3x squared plus 4z. So the x changes into r cosine theta. So we have 3r squared cosine squared theta. The plus 4z does not change. Okay, z does not change. In the integrand, z is independent of x and y. Okay, and that might annoy you because why did we change the z, the x and the y over here in our limits? Okay, because these are part of the domain. Okay, so this surface depends on x and y. This function, in this function, z does not depend on x. Okay, z is an independent variable in this function. Okay, that's a subtle point that sometimes can be confusing or annoying in this case, I guess. Okay, so we set up our triple integral. Don't forget the extra r in the r dr d theta. Okay, so we integrate with respect to z first. We can leave the r out because it's a constant with respect to z. So we have an extra z in the first term. 4z turns into 2z squared. Okay, and then we have to plug in our limits. So 9 minus r squared goes into our z. So we have this and into the z squared. So we have this and we have, we put the extra r right next to it, which we will account for in the next step. Okay, so I changed my mind. Instead of going to the next page right away, I wanted to show you that r will combine with the r squared, give you r cubed, but it's going to be shared with the 9 and the r squared. Okay, so r cubed goes with the 9 r cubed, and with the r squared, so r to the 5th power. Okay, so that is what we see in this next line. If you're following along in the book, you see it right away. Okay, so now we will integrate with respect to r, and we will get for the first term 9r to the 4 over 4 minus r to the 6 over 6. So that's the easy part. What about the second part? Okay, so that one, we need a small u substitution. If u is 9 minus r squared in here, then du is negative 2r dr. Okay, so how would you integrate positive 2r times this with the dr? Okay, you just lose the negative. Okay, how convenient. So we have u squared, negative u squared. Okay, so that will be negative 1/3 u cubed. Bring back the 9 minus r squared for our u. Whew, okay. So now we can plug in the limits from 0 to r. And you always have to be careful with 0, okay, because sometimes, many times, it goes away. Sometimes it doesn't, and that's when you spend half an hour looking for your mistake. Why am I wrong? So at 3, we have 3 to the 4th here, 3 to the 6th here. That's straightforward. 3 squared is 9, so we get 9 minus 9. That's going to be 0. Yay. Okay, now what about 0? So we will get 0 and 0 here. Thank you. The first term is completely 0. And then you'll get plus 1/3 9 minus 0 squared. Ooh, so that's 9 quantity cubed. Okay, so that part is not 0. Okay, very easy to make a mistake there. So arithmetic, this becomes, and there's a times 3 there, which I forgot the first time I was writing this. Ugh. And we get 729 over 4. It's very easy to lose the constants. Okay, and this becomes 243. Okay, so by the way, when I make these computations, I ask Maple to compute from the very top, from the setup, what should be the correct final answer. And when I get down here, I'm like, that's not the final answer. I have to step-by-step check, did I make the mistake here or here or here? And it helps, of course, to make Maple compute these integrals step-by-step for me. Okay, so now, power reduction, cosine squared is 1 plus cosine double angle, 2 theta over 2. And what are we going to do? We get a fraction here, 729 over 8, and then a 243 outside. Okay, so I prefer to put them together as a single constant. Okay, you might want to just leave them separate and integrate them separately. That's up to you. Okay, so we have now for the cosine 2 theta term 729 over 8, theta and therm, right? Okay, so we can integrate that very easily and get an extra theta here. Cosine becomes sine 2 theta over 2, so over 16. However, we are going from 0 to 2 pi. Okay, so at 2 pi, theta becomes 2 pi. Sine 4 pi, 0, thank you very much. Theta is 0, that goes away, that goes away. So we are left with 2673 over 4 times pi. Oh, yesterday was Pi Day, so happy Pi Day. All right, so here's the more complicated example, and we get to play with this diagram in GeoGebra. So we want the triple integral of 5x plus 2y over the solid E, where E is the region in space, which is inside this cylinder, x squared plus z squared equals 16, and which is in front of the portion which is in front of the YZ plane. Okay, so Y versus Z. So basically, it is the front half of that cylinder. But we also want the part to the right of the XZ plane. Okay, so where Y is positive, but we want it cut off at the slanted plane 5y plus 6z equals 30. Okay, so we want the portion to the left of that plane. Okay, so if you go to GeoGebra and you input this cylinder, and you get y equals 0, and of course x equals 0, and you enter this plane, you're going to get this diagram. Okay, so that's not a very satisfying diagram by any means. Okay, so we'll go on to the next page, and then we'll see a nicer version of it. Okay, so the first step to making a satisfying diagram is to work on the cylinder. Okay, so it's very easy to turn the cylinder into a parametric surface because it's basically a circle moving along the y-axis. Okay, so I decided to make as our parameters, as usual, u and t. U will go from 0 to 12, and it will represent the y-coordinates. So notice that that's green over there. Okay, and that's our x-axis. Okay, so u will go from 0 to 12. X and z will be our essentially polar coordinates. Okay, because our cylinder is x squared plus z squared equals 16. Was it? And yes, thank goodness, it is 16. Woo! Sometimes it's easy to confuse radius 4 and right side equals 4. Okay, it happens to me all the time. All right, and then when we cut this cylinder with the plane, then we can see it a little bit clearer. Okay, like this. All right, so the coup de grace is to make the cylinder stop at the plane. Okay, that's a tricky part. And then we want the plane to be only within the cylinder. Okay, that is also a somewhat tricky part. Okay, so we have the nicer diagrams right here, and we can see the surface commands. Okay, so I believe this is the surface command for the cylinder, correct, because we have 4 cosine t, 4 sine t over here. Notice u is gone. U is now gone, replaced with v, okay, which is only going from 0 to 1. Okay, now why is that? Remember when we did this before, where we use v to stretch a vector from 0 to its full desired length. Okay, and also notice that we only are taking part of the cylinder. Okay, it was you know, a whole can before, but now we're only taking the part to the right, and you do that by restricting the parameter t. Okay, so if you want the right half of the circle in x and z, then you'll make your theta go from negative pi over 2 to positive pi over 2. Okay, so let's go to GeoGebra and play with this diagram. All right, so here on the left, you can see the instructions to surface that I used to make this diagram. And yeah, well, now we can turn it around as much as we want, and we can see how to treat it as a polar region. Okay, so the trick, of course, is to look at it from the side. And there we see that x is on the right, c is going up, surgeon hands, right on. Okay, there we go, almost. And lock it, yaha. Okay, so we have the right half of a disc, okay? And of course it is radius 4 over here. You can see the green arrows here, all right? So we still have to think in terms of type XY, type YZ, type XZ. In this case, it is a type XZ solid, okay? Send arrows through that solid, and you will enter at y equals 0, and you will exit on this plane, this inclined plane, okay? So the nice thing about drawing these using surface is that you can literally see what the domain of the double integral should be, okay? So they go hand in hand, understanding the solid and understanding how to create the surfaces that make up that solid, Okay, so theta is going from negative pi over 2 to positive pi over 2, as we said. 0 is, 0. R is going from 0 to 4. Okay, so you can see in this diagram how the grid lines are being traced on this half disk. That's polar coordinates. Okay, and similarly also on this plane. I used polar coordinates in order to make that plane. Okay, so now we can go back to our workroom and set up that integral and crank it out. All right, so here is the XZ test that we just saw, and that tells us that we should have X and Z converted into polar coordinates. Okay, so you might wonder, why does cosine go with X and why does sine go with Z? Okay, so in this case, it's the natural way to do it because of the geometry. Okay, we want the right side of the disk, so it's natural to make X with your cosine and your Z with your sine. Okay, so theta is going from minus pi over 2 to pi over 2. R is going from 0 to 4. Okay, so our arrows enter at the at y equals 0, and we exit on the plane. Okay, but what was the equation of the plane? Let's go back over here, and on the plane, scroll up. The plane is 5y plus 6z equals 30. Okay, so we are doing type xz, so we have to solve for y. Okay, so y equals 30 minus 6z over 5. Okay, so, whoops, I think I went too far, a bridge too far, and there we go, my apologies. So y is 30 minus 6z over 5, so as usual, convert z into polar coordinates. Z is where we assigned our sine theta. Okay, so yeah, as I was saying, these are exactly the conversions that you need in order to create the half disk and the semi-ellipse. Okay, so the instructions are over there, even if you don't have the GeoGebra file, which is only for my students, just kidding. You can also recreate it on your own and change the colors. Okay, so fasten your seat belts. This is going to be a little bit more complicated than our first example. So we have 5x plus 2y as our integrand rather. Okay, and we have theta and r as usual on the outside, minus pi over 2 to pi over 2. 0 to 4. Don't forget the extra r over there. Y from 0 to over here, which we computed above. And our integrand, x is where we assigned r cosine theta. Okay, plus 2y. Our inner integral is dy. So when we integrate, we will have an extra y on the first term, and 2y turns into r squared. Then we have to plug in the endpoints. Okay, thank you. 0 goes away. Y goes, is replaced by this. So we have this plus this squared. Okay, so there is, of course, a common factor of 6 in here. So we can take it outside along with the 5 to make 36 over 25. Okay, and that 6 also goes out over here. 5s cancel. Okay, so I kind of chose the coefficients so that the arithmetic is not so horrific. Okay, it's bad enough as it is. Okay, so we have to, so we have a 6 here and a 36 here, so we can take out a 6. That makes the numbers also a little bit smaller. So we have 6 over 25 instead. We have to square that. Okay, so, we're going to get 25 minus 10 r sine theta plus r squared sine squared. I distributed the 6 over 25. Okay, so we have these terms, and then we keep going. Let me just scroll down to the bitter end. Almost there. Okay, so we were over here, and then we factor in, multiply in the extra r. So r squared r cubed, 6r, r squared, r cubed. Okay, and then we are ready to integrate with respect to dr. So 5/3 r cubed, 1/4 r to the 4th, 6r turns into 3r squared, r squared into r cubed over 3. Where did the 3 go? Cancels with the 12. There's a 4 over there. And then r to the 4 over 4. So 2 cancels with 6. You got a 3. There's a 2 left there. We get 50. Okay, I do believe I checked this as well. Okay, so now we plugged in 0 to 4. Do we have to worry about 0 this time? Thankfully not. Okay, all the r terms disappear at r equals 0. Okay, so now how about r equals 4? So 4 cubed, 4 to the 4, 4 squared, 4 cubed, 4 to the 4. Okay, so that step is of course just arithmetic. And now what do we have? We have sine squared as the nastiest term. And yeah, we perform our power reduction in that case. So we have 1 minus cosine 2 theta over 2 this time. And no change, no change. 48 I combined with 384 over 2 will cancel, and over 25. So I combine those two numbers into that single number over here. Sine theta doesn't change. And this becomes minus 192 over 25 cosine 2 theta. Okay, so we are now ready to integrate this with respect to theta. Cosine becomes sine. We have a nice u substitution here. Haha. So that is u, and there's a du there. So u squared over 2. And then that just gets theta. Minus sine becomes plus cosine. How convenient. And double angle minus cosine becomes minus sine. Now there's a 1/2. So we have a partial cancellation with 192 turns into 96. Okay. Now we have to be really careful about plugging in negative pi over 2 and pi over 2. Okay, so for that, I use my technique of doing it term by term in pairs instead of do pi over 2 by itself, do minus pi over 2 by itself, then subtract. Okay, when you're dealing with several terms like this, I prefer that style. Okay, it's up to you, of course, what you do. Yeah, that minus sign is always going to be the source of mistakes. Okay, so that's why I like to keep them close together, because you're doing the subtractions right next to each other. Okay, so sine pi over 2 minus sine of negative pi over 2, that minus sine negative turns into a plus. Okay, sine squared theta, okay, now it's positive. Okay, so 1 minus 1, that goes away. Theta, pi over 2 minus minus plus pi over 2. How about cosine theta? Ooh, cosine pi over 2 and negative pi over 2. Both 0, thank you very much. Double angle, sine of pi, sine of negative pi. They are both a 0. Okay, so go away, that doubles, go away, that doubles. Okay, and then don't forget to multiply by 6. Okay, so we get this as our final answer. Oh, wait a minute. I need to be honest with you. I have a little typo over here, which I'm going to correct now. I put in an extra 0 over there. So that should just be 640, and that should just be 128. Okay, so now let's go to our workroom, and I will give you an example, a fresh example, and we will compute a triple integral from scratch. All right, so here's a fresh example. We want the triple integral over e of 4x plus z squared dv, where e is a solid bounded by the cylinder, y squared plus z squared equals 9. And the planes x minus z equals 1 and x plus z equals 8. Okay, so I have GeoGebra open on the side over here. Let me make sure that those are my correct planes. Yes, they are correct. All right, so I'm going to take you to GeoGebra now, and we're going to see what this solid looks like. Okay, here we go. So I'm just going to give you a bare bones diagram here. Just input the 3 equations. And we get our solid over here. It almost looks like a candle lying down, doesn't it? Okay. So we have the cylinder, which is in Y and Z. So if you look at it from the front, okay, so there is Y versus Z, okay? But it's going to be cut by these 2 planes, okay? So notice that instead of Y and Z, we have X with Z on these 2 planes, okay? So notice how they're kind of sloping in different ways, okay? So yeah, if you look at it from the side view, okay, make the Y disappear. Ooh, okay, so that's your side view. So one plane is going this way and the other plane is going that way, okay? So notice that I had to make sure that they intersect outside the cylinder. Okay, that's very important because if this plane, for example, were lower, then yeah, your cylinder is cut off. Okay, so would that be impossible to do? It would be trickier. Okay, I must admit it would be a lot trickier. You probably have to solve for different boundaries if that happens. So this is a much safer example. Okay, keep it simple. Okay, so how are we going to treat this solid? Okay, over here. Should it be a type XY, type XZ, or type YZ? Okay, so the trick, of course, is to find the view where we see a polar rectangle. A circle will be nice. Top view, I don't think so. How about the front view? That is where we see a circle. Yes, you got circles. Okay, so of course the circle disappears if we look at it really from the front. So there's Y, there's Z. So yeah, you got to tilt it a little bit over here. So it's kind of like a tunnel, okay? A circular tunnel, an empty can of dog food or something. Okay, so we have to treat it as a YZ solid, okay? And it looks pretty simple, okay? It's just a disk, so we know exactly what to do. It's kind of like our first example, okay? So we will let our Y be our R cosine theta. Our Z will be our R sine theta, okay? Theta, full circle, 0 to 2 pi. R, the radius is 3, so R is going from 0 to 3. Okay, easy enough. Now, what about the inner integral? Okay, that's a type YZ solid, so it's X that we need to worry about. Okay, so the arrows will be coming towards us parallel to I, in the same direction as I, and it enters through this plane and exits through this plane. Okay, so which plane is which? Okay, so it enters through this plane, and oh, I see an 8 over there. That must be because of that 8 over there. Haha. So this plane is our first plane, and this plane is our second plane. Okay, so this will be where we enter the solid, and this is going to be where we exit the solid. All right, we know everything. We are ready to set up our integral. Okay, so here we go. Before we forget, let us write down our observations. We will enter at this point. Okay, so of course we have to solve for x because we're doing type YZ. So x equals 1 plus z. And we exit at this point, this plane. So x equals 8 minus z. Okay, so those are our limits to the inner integral. Okay, so now let's put in our limits for r and theta and our conversions. Okay, so we said that y will be our r times cosine theta, and our z will be our r times sine theta, sine theta. Okay, and what are our domains? So theta will go from element thereof. Where's my element? There you go. Theta will go from 0 to 2 pi. Happy Pi Day. And r will go from, what did we say? 0 to 3. Excellent. All right. So we have to use these conversion formulas in our entry and exit surfaces. So that would be 1 plus r times sine theta. Okay, there we go. And then 8 minus z, so that is going to be 8 minus r sine theta. Okay, that's the hardest part. Okay, finding out what are our limits for the double integral, polar coordinates, and for our inner integral. Okay, x in terms of y and z. In this case, it only depends on z, so in terms of r sine theta. Okay, so now we are ready to compute our triple integral. It's raining outside, so beautiful. We need the rain. We are below our usual levels. Okay, so now we will set up our integral. Theta on the outside, always a safe bet. So theta will go from 0 to 2 pi. Okay, and what I do is I put in the differential there, put in my parentheses, so I have everything inside. Okay, and then we have r. R going from 0 to 3. Okay, and to be safe, I put the r in here and the dr out there. Okay, Maple doesn't like that times symbol. Okay, so I don't put it in because we want to check our answer, right? Okay, and then on the inner integral, we now have x. Is that right? Yes, x. So x is going from 1 plus r sine theta to x equals 8 minus r sine of theta. Okay, our integrand is 4x plus z squared. Okay, so, and our variable of integration is dx. Okay, so 4x does not change. I can copy this whole thing over here. But the z squared, z is our sine theta. Okay, so let me borrow this over here because I don't want that dot. So z squared, r squared, sine squared theta. Okay, there you go. That's our setup. And once that's set up, it's basically on autopilot. Okay, shall we find the answer? Okay, so delete, delete, and delete. Okay. I hope it doesn't blow up. Haha. So do we have an answer? Ooh, interesting. 5103 over 4 pi. Okay. So, how do we get there? So from the inner, okay, the inner integral is going to be this. So 4x, we have a dx, so that is 2x squared. Okay, and we have an extra x. Okay, so let me put an x over here. Okay, we are evaluating from here, here. Okay, so yeah, it's always those squares that are annoying, right? So let's do this. Okay, so we did want this squared minus the bottom also squared. Okay, so yeah, this point is algebra. If you're doing this on your own, you might want to apply that trick we learned back in chapter 2, I think. Okay, so a squared minus b squared, a minus b times a plus b. Okay, the nice thing about it is that you only have one product. Here you have two. Okay, so yeah, then what is the answer? Oop, that's a lot of help. Thank you so much. So compute and expand. Ooh, okay. So very interesting. Oh yeah, check it out. There's no squares because when you do the trick, it disappears. Okay, so when you subtract, you get 7 minus 2r sine theta. And then when you add, you get 9 plus 0. Haha, right? So yeah, instead of squaring individually, it makes so much sense to use a minus b times a plus b. So that's just 63 minus 18r sine theta. Ooh, lovely. Okay, and for the other one, we have to multiply by x. So guess what? We will need this minus this, so we have this. Okay, so we are going to have, okay, so what is our antiderivative? We need 2x squared, so 2 times this. And then we will have r squared sine squared theta times x. Okay, so our x is going to be this minus this, but that's what we did over here. Okay, so see, there is an advantage to using the a minus b times a plus b. Okay, so little tricks that you can use. Okay, so we have some algebra to do. Okay, we still have to distribute that. Okay, so compute, expand. Yeah, okay, so there we go. Okay, so yeah, we do get something which is a little bit more complicated than we had before, but I have a feeling we did integral sine cubed already sometime in the past. Okay, so yeah, and of course, okay, at this step we also have to have that extra r. Okay, so if you multiply that by r now, this, and then times r, we will get, compute expand. Okay, so of course every term gets an extra r. Okay, so we are ready now to plug that into our double integral. And again, just so we can check, okay, so this now goes in here. Yeah, so we will delete that, and we have this. Okay, so do we get the same answer? Are we on the right track? Yeah, this is how I write my I'm writing my ebook, because yeah, it's a little bit embarrassing when you get to the end, like, wait, that's not right. So let's check. Are you correct so far? And yes, of course, we are on the right track. All right, so I'm actually going to, it's already 45 minutes, so I'm actually going to let you finish off with the numeric computation. The r's are not difficult at all. It's the sine cube which is difficult, right? Sine squared, power reduction, we just did that, okay? So how do you do sine cubed theta? just as a reminder, I feel like we've done it, but maybe not. Okay, so what is sine cubed theta d theta, antiderivative? So the trick is to borrow a sine. Okay, so we will have sine squared theta, and then we will have an extra factor of sine theta. Okay, maybe you remember this from your second semester calculus class 5B. Okay, so we did that because now we can use the Pythagorean identity. We will change sine squared into 1 minus cosine squared theta. Okay, and we distribute. Okay, so I'll do it next line. So we now have sine theta in here minus cosine squared theta times another sine theta. We know how to integrate sine theta. What about this? We need a new substitution. Okay, so if u is our cosine theta, then our du will be negative sine theta d theta. Okay, so that's convenient because there's a minus over there. So that is a plus u squared du. Okay, so integrate, that's going to be 1/3 u cubed. Okay, let's enter derivative of sine, that is minus cosine. Okay, so plus, yes, so plus u cubed, so it's over 3, so plus 1/3 of cosine cubed theta. Okay, there you go. So that is how you integrate sine cubed. Okay, I wonder if Maple agrees with me. What, oh, all-knowing one, what is integral of sine cubed? Ooh, fancy, triple angle formula. Okay, I'm not sure how it did that. Okay, but we're not sure. How about compute, calculus, implicit differentiation? I don't think I've shown this to you before. So we'll differentiate with respect to theta. Okay, so we get that, and of course I see sine theta factorable outside, leaving 1 minus cosine squared, which is sine squared. Sine squared times sine theta, sine cubed theta. Okay, there you go. So you got some homework to do if you want to do it, or you can just jump directly into our exercises. Maybe that's a little bit more efficient. Okay, you know how to do this integral, I would think. All right, so that is our video for today. I hope you enjoyed polar coordinates one more time. And next time, we will look at a very different kind of coordinate system called the spherical coordinate system. Ooh, spheres. Okay, there will be again angles involved aside from spheres. Okay, so until next time, thank you very much for watching my video. Enjoy the rest of your day. Bye-bye.